Welcome to The Explainer. Today, we're taking a look at something that feels like, like the universe's secret source code. It's a hidden mathematical language that describes pretty much everything, from a ripple in a pond to the chaos of the financial markets. So, what is this incredibly powerful, invisible engine? So, think about this for a second. What could possibly connect the way a sound wave travels, the way heat spreads from a hot stove, and the way financial markets seem to unpredictably swing up and down? I mean, they seem totally unrelated, right? One is physics, one is thermodynamics, the other's, it's about money. But what if I told you that a single, powerful mathematical idea ties all of them together? Well, that idea is partial differential equations, or PDEs for short. And simply put, they are the language that science uses to describe change. Not just that something changes, but how it changes across both space and time, all at once. They really are the hidden engine of modern science. And today, we're going to pop the hood and see how it works. So here's our game plan. We'll start with what these things even are. Then we'll see how they were born out of real-world problems. We'll explore how they became this beautiful obsession for pure mathematicians. And then we'll witness their incredible impact in the 20th century. And finally, we'll look at what's next for them. Okay, so what are these things, really? I think the best way to wrap your head around PDEs is to think of them as this powerful, two-sided engine that's been driving science forward for more than 200 years. The brilliant mathematician Henri Poincaré, he really hit the nail on the head back in 1890. He noticed that all these wildly different physical problems, things like heat, magnetism, how things stretch, they all had what he called a family resemblance. He was seeing the first real clues of an underlying shared language that connected everything. And that language was PDEs. And this gets us right to the heart of that two-sided engine. See, on one side, you have the drive for application. Scientists, engineers, they need to solve real-world problems. On the other side, you have abstraction. This is where pure mathematicians become fascinated by the beautiful, elegant structures of the equations themselves. And for centuries, these two forces have been pushing each other, creating this amazing cycle of innovation. All right, let's jump back in time to the 18th century and see how this all got started. You see, PDEs weren't just dreamed up for fun in some ivory tower. No, they were forged in the heat of trying to solve some of the most urgent scientific puzzles of the era. It actually all started with a pretty simple question. How do you write down the math for a vibrating violin string? In 1752, a guy named Jean d'Alembert figured it out, and in doing so, he created the wave equation. This was one of the very first, most fundamental PDEs, and it gave us a formula for how waves move through space and time. Next up, another huge question of the day. How does heat actually flow and spread out? In the early 1800s, Joseph Fourier cracked that code with his famous heat equation. It's this incredibly elegant formula that perfectly describes how heat dissipates from hot areas to cold ones. It's still a cornerstone of physics today. Then you've got the third of the big three from this era, from Laplace. And his equation tackled a totally different idea, equilibrium. It was first used for gravity, but then scientists had this aha moment. They realized it could describe any system that has settled into a steady state, from electrical fields to the flow of water. The sheer versatility of these equations was just becoming impossible to ignore. And it wasn't just those three. The next century was just this gold rush of new equations. You get Euler's work on fluid flow, then the Navier-Stokes equations for fluid dynamics, and then the really big one, Maxwell's equations. He used PDEs to unite all of electricity, magnetism, and light into one single beautiful theory. At this point, PDEs weren't just a handy tool anymore. They were becoming the fundamental language of physics. But then, something really interesting started to happen. The tool itself became the treasure. This is the other side of our engine kicking into high gear. Mathematicians started studying PDEs not just for what they could do, but for what they were. This whole shift was really led by people like the legendary Bernhard Riemann. He realized that the solutions to these equations had these strange and fascinating properties all on their own. He started using them as building blocks to create entirely new areas of abstract math. It was like he was turning a physicist's hammer into an architect's blueprint for a whole new mathematical world. And this brings us to the 20th century, which is where our two-sided engine just goes into complete overdrive. All that abstract mathematical machinery that Riemann and others had been building, it suddenly turned out to be the perfect language to describe the huge scientific revolutions of the new century. Application and abstraction came back together, and the result was, well, it was spectacular. Just look at this explosion. Suddenly, all that abstract math found a home. The bizarre world of quantum mechanics? Turns out, it needed something called functional analysis, which grew out of PDEs. Einstein's general relativity? It is literally written in the language of partial differential equations. Even something as modern as financial modeling, pricing stock options, it was cracked using a blend of probability theory and PDEs. This reunion was like a big bang for science and technology. So, where does all of this leave us today? What's the next frontier for this unbelievably powerful tool? By now, you can see the pattern, right? This engine of discovery we've been following. A tool is born from a real-world need. That tool inspires a whole new area of pure math. And then the two come back together to completely revolutionize everything. And that engine is absolutely still running today. Hey, remember Poincaré from the beginning? In that same paper from 1890, he made this incredible prediction. He said that because these equations were so complex, we would eventually need massive computation to help us solve them. And wow, was he right? Today, many of the most important PDEs, the ones that forecast weather or design airplanes, can only be solved using gigantic supercomputers. But that doesn't mean we've solved everything, not by a long shot. The problem of turbulence, that chaotic, swirling motion you see in a raging river or even in the smoke from a candle, that's described by the Navier-Stokes equations. But a full mathematical understanding of it remains one of the great unsolved problems in all of science. It's actually a $1 million prize problem, and PDEs are sitting right at the heart of it. So from a simple vibrating string to the structure of the entire cosmos, from the atom to the global economy, partial differential equations have been the silent, powerful engine driving discovery. So the final question is, what's next? What seemingly impossibly complex system, maybe the networks in our own brains, maybe consciousness itself, is just waiting out there for the right equation to finally unlock its secret?